pleasure to introduce the third and final speaker of the morning. And it's Gabriel Ponce, who'll talk about metric and ergodic properties of partially hyperbolic diffeomorphisms with topological neutral center.
Hi, everyone. So first of all, thank you all the organizers for the organization of this beautiful conference. It's my first time in Poland. And yeah, I'm enjoying very much the center, all the atmosphere of the conference. And also thank you for the opportunity to talk here. So I will talk a little bit about partial hyperbolicity. I know that some people have spoken about it in the conference, so I will be kind of brief with the basic definitions. But of course, if you have any questions, I know that some people just arrived in the conference. So if you have any questions about the basics, feel free to ask. Okay, so just to fix the setting, I will kind of stand very close to the people here to see the slide. But just to fix the setting, all along the talk, M will be a smooth remaining manifold, and all along the talk, mu will be a probability measure. Sometimes I will have this measure to be a smooth measure, but a priori, it's just a Borel probability measure on M. And I will take F to be a C2 partially hyperbolic. Yeah, I know, but I'd like to point. So, and F will be a C2 partially hyperbolic diffeomorphism. And by this, I mean that I have a splitting on the tangent bundle. So the S direction here is called the stable direction. The U direction here is called the unstable direction. And the C is called the center direction. And these directions have contracted behavior, expanded behavior, and the center one is dominated by the other ones. So this translates in mathematical terms to these things. For large iterates, the derivative of F along the stable direction is less than a half. So here I'm taking any vector, any unit vector in the stable direction. The derivative of the past of F along the unstable direction is less than a half. So this gives the sense of expansion. And we have the domination. So the domination, for example, between the stable and the center means that the derivative along the stable direction is less than a half of the derivative along the center. And the same holds for the center and the unstable direction. So that's why we have this 1/4 here. Pointwise, yeah, everything's pointwise here. Yeah, here I'm assuming all three bundles are non-trivial. Okay, so I'm gonna go straight to the definition of topological neutral center. So first we have the definition of Lyapunov stability. So we take just a single bundle of the bundle of M, and we say that F is Lyapunov stable along this bundle if whenever you fix a very small value, epsilon, you can choose like very small arcs of size delta, such that these arcs cannot grow more than epsilon when you iterate forward. So here I'm just taking forward iterates. And okay, it just means that if you take an arc tangent to a certain direction, and if this arc is sufficiently small, it will not pass the epsilon size. And I say that F has topological neutral center if both F and F minus 1 has this property, has Lyapunov stable center. So gamma is a curve tangent to this bundle. Everywhere, yeah. In every point of gamma, it is tangent to E. Okay. Sorry? Yeah. Yeah. And then if we have this property for F and F minus 1, we say that F has topological neutral center. I mean, here by taking this E to be EC. So this means just that if you take arcs tangent to the everywhere tangent to the center direction, and if these arcs are small enough, forward and backward iterates of these arcs cannot grow too much. We don't know how this epsilon and delta relates, so it's not it does not mean that the derivative of all Fn are bounded. So this is something that I will give some examples later. Okay, so this property was appeared in the exactly. Where is what? The curve is in the manifold. Yeah, it's in the manifold. It's tangent to, let's see. No, I mean this distance is just inside the it's just the length of the curve in the manifold. So you take the remaining, yeah, it's the length. You take the remaining distance in the, yeah, this is not. It's just you take the remaining manifold, you take the distance in the remaining manifold, and yeah, and you take the length in this, like this distance. No. So this definition is general, although I recognize my draw is one-dimensional, but this definition is general. Okay. No, the curve is in the manifold. Yeah, exactly. Yes. Yes, sorry. I was trying to make this a little bit more concise. I understand that it's a little bit confused, but this is right. I mean, it's for every gamma. So for every epsilon, there exists a delta such that for every gamma tangent to this E, yeah, exactly. Then this happens. Burns, do you have a question? No. Okay, so Lyapunov's stable property appeared sometimes in the literature. For example, because we know that the stable and unstable directions integrate to invariant foliations, but the center direction does not integrate to an invariant direction. But this Lyapunov stability property guarantees that your system is dynamically coherent. So this is a result that is in a survey of Hertz and Neuers. So, and by dynamical coherence here, I understand that there are two invariant foliations, which are tangent to the center stable and center unstable bundles. And this will induce a center direction, which is just the intersection of these two foliations. So you have a center foliation tangent to the center direction. And also it implies Planck expansiveness of the center. I will not define this property here, but it's just important to know that this property is robust. So it's not C1 perturbable. And it also guarantees that whenever you perturb partially hyperbolic diffeomorphism, which is Planck expansivity along the center, you have leaf conjugacy with the diffeomorphism that you have perturbed. Okay, so it was believed for some time, it was called Pujal's conjecture, that three-dimensional partial hyperbolic diffeomorphisms would fall into these three categories. And by fall in these categories, I mean that up to finite covers and iterates, you could find a leaf conjugacy between this map and one of these three kinds of maps. And these are linear Anosov automorphisms on T3, skew products over a linear Anosov map on T2, and time one maps of Anosov flows. And it was proved by Bonatti, Parwani, and Potri in 2016 that this is not true. So they gave examples, the first examples of maps that do not fall in this classification. There are several generalizations of these results, but in this first example, for example, in this first case, the diffeomorphisms have this neutral center property, which is stronger than topological neutral center. The derivative, they are not transitive. No. Yeah, the reason will appear a little bit later, but the first examples are not transitive. Yeah, I didn't know that. I thought the conjecture was in general. It was for transfer. Yeah, but do you have examples of transitive? Yeah, okay. It's just not in that paper, right? Yeah. Okay, yeah. Yeah, sorry about that. I just put this one, but there are several other generalizations by then. Okay, so I will not enter in this construction, but it's just important to know that these new examples have this topological neutral center property. Actually, they have a stronger property, which is called neutral center. The derivatives of Fn are bounded by below and above. So this implies that the curves cannot grow up to k times the original size of the curve and cannot become smaller than 1/k size, the original size. Okay, and it's natural to ask if this property, if this neutral center property is equivalent to topological neutral center, because this is much stronger. I mean, you can compare it somehow to an isometry. But this is not true. So the example that I will give is by Bonatti and Zhang. You take a linear map, an Hausdorff linear map on Tori, and then you put S1 as fibers. And on the fiber, you take a map with C1 close to irrational rotation. So this is just to make the product and guarantee that it's partially hyperbolic. But we take this map in such a way that if you take high iterates of this map, then you can find points for which these iterates are very large. And the existence of such maps is guaranteed in a work of Bonatti, Purvis, and Wilkinson. It's in a lemma. And also this map is C0 conjugate to the irrational rotation. So because it's conjugate to the irrational rotation, we have the topological neutral center property. You just pull back the matrix preserved by the irrational rotation. But you don't have the neutral center property because the derivatives are not bounded. So this is an example of a partially hyperbolic diffeomorphism. It has TNC property, and it's transitive because the basis is topologically transitive and the fiber is transitive as well. Okay, so looking for the topological properties of this kind of maps, we have several recent results. So the first one I will mention is by Zhang, where he classified the types of center stable and center stable leaves of this kind of maps in 3 dimensions. So if the manifold has 3 dimensions, then each leaf of the center stable foliation is either a plane, a cylinder, or a Möbius band. And the last 2 cases can only occur if you have a compact center leaf inside the respective leaf. And this classification is robust because the topological neutral center property implies center expansiveness. And so if you take diffeomorphisms which are C close to this one, they have leaf conjugacy with this map. Okay, and then in 2020, Bonatti and Zhang classified all this kind of diffeomorphisms which are transitive and are in a 3-dimensional manifold. So they proved that actually these diffeomorphisms up to finite leaves and iterates, they are C0 conjugates to one of these 2 models. So there is a model kind of missing here from the previous 3 types of models, which are derived from a knot of diffeomorphisms on T3. They are missing here because actually they do not have topological neutral center. So it's impossible to conjugate with that model. Yes. Yes, all of them. Yeah. Yeah, and all along I will assume from this part that the dimension of the center is 1. Okay, so a very important part of the talk will depend on this result, which is actually the result that they used to prove this previous one. And this is for general dimension of the manifold. So if you have, again, partially hyperbolic, center dimension 1, and topological neutral center, and you have transitivity for F, then you can find a continuous system of arc lengths which are invariant by F. And by a continuous system of arc lengths is invariant by F, I mean that we have some maps, Lx, defined on simple arcs of the center. And these maps give positive value to non-degenerate arcs and give zero value to degenerate arcs, which are just points. They have, oops. Taking a Nosov map and then North Pole, South Pole. No, I think it's not. You take like curves on the North Pole, for example. Yeah, it will grow. No, yeah, it's not that they stay bounded. You can choose the boundedness constant. Yeah. Yeah, it is stronger. So yeah. Okay, so you need to have this positivity on non-degenerate arcs, and you need to have this additivity. So if you take a concatenation of arcs, then the length of the whole arc is just the sum of the arcs that are being concatenated. And we have F invariance. So this means that if you take a curve, which is tangent to the center direction everywhere, and you take the iterate of this curve, the length will be equal to the original with respect to this arc length system. And because of this system, because of the continuity of the system, it will be also invariant by stable and unstable anomalies. So you can take one of these maps and you take, for example, Lx, you go with this by a stable anomaly, you induce an arc length in another center leaf, and this will be equivalent to the original one. Okay, so passing now to the smooth ergodic scenario. So in the smooth ergodic theory, we are kind of worried about this kind of problems. So you wonder which geometric structures impact on the ergodic properties of your map and how this impact occurs. And also on the geometry of the invariant probability measures in terms of how these measures, for example, disintegrate along the invariant foliations. In this direction, we have several results. I will not detail them here because they have a lot of hypotheses that I do not have time to show. But of course, I have missed some names, so I'm sorry if someone is in the audience and the name is not here. But just to summarize, for example, Spatsievich studied equilibrium measure for isometric extensions of Nosov systems. If you have an isometric extension of an Nosov system, then in particular, you have topological neutral center property for this map. And Kleimenhaga, Passing, and Zeletovich proved the uniqueness of equilibrium measures for certain potentials and also obtained the structure of such measures. And here it's important to say that they do not use topological neutral center. They use just Lyapunov stability of the center stable manifold. And a little bit further, Lee and Wu proved that Bernoulli property for these measures that were obtained in this work. And more recently, Carrasco and Hertz, using a different method from Kleimenhaga, Passing, and Zeletovich, proved uniqueness of equilibrium measure for certain center isometries for certain holder potentials, and also studied the structure of such measures and proved that they are Bernoulli. Okay, so just to say very briefly, there are some intersections between these works, but the difference is that some of them works for more general holder potentials, some work for less general holder potentials, and also the conclusions on the structure of the measures depend on the hypothesis. So in this case, since they have center isometries, the conclusions are a little bit stronger than the ones that you can get here. Since you don't have center isometries, the hypotheses are a little bit weaker. Okay. And it's fundamental that in all of these works to obtain the uniqueness of these measures, you need to understand the disintegration of these measures along the invariant foliages. Okay, so going a little bit back in time, we have this very celebrated result from Bernoulli and Wilkinson, where they show that for C2 partially hyperbolic diffeomorphisms preserving a smooth measure, if you have center-bunched hypothesis essential accessibility, then the diffeomorphism will be ergodic. Actually, it will be homograph. So just to say very briefly, I will not say what this property is, but since I'm dealing just with one-dimensional center here, it's important to know that this property holds. Essential accessibility just means that if you take any measurable set for which any two pair of points can be connected by an unstable and unstable path, then this measurable set should have either measure 0 or 1. And the Kolmogorov property, I was not too much worried about it because I was supposed to give my talk on Tuesday, and I know that Gabriel will talk a lot about this property. So I was just about to say that, okay, after my talk, she will say a lot about it. But actually, it's just important to know here that it's equivalent to a kind of uniformly mixing. I will not use the details of this property too much. It is equivalent to a type of uniformly mixing property. So it's stronger than ergodicity. Okay, and then there is a problem attributed to Burns. It was asked in a conference in one of those compilations of problems. Are these diffeomorphisms Bernoulli? This is a very natural question because usually in theory, when you have some kind of hyperbolic structure and you have the Kolmogorov property, this will imply the Bernoulli property, which is stronger than the Kolmogorov property. Bernoulli here just means that it's measurably conjugates to a Bernoulli shift. And this is probably very hard to solve. Probably the answer is no, but it's not easy to think about a counterexample for that. And there is a more approachable problem, which is on Hertz-Hertz-Uly's survey. It's attributed to Emmy. That is the same question, but assuming that F is Lyapunov stable along the center. So there is a reason for this thing to appear here. It's not like just random, because we will see that to go from Kolmogorov to Bernoulli property, we kind of need to have some control on the growth of the center direction. Okay, so the following results I will show are related to these questions. So the first one is a result together with Alita Zibi and Regis Varão. It's not new, but I want to show here because it contracts a little bit with the other one. So this first result is for derived Foronozov maps. Assume you have a derived Foronozov map on T3. So this means that it's isotopic to a linear Foronozov map. And assume it's volume preserving and partially hyperbolic. And here I'm assuming the center Lyapunov exponent to be negative. This is not exactly a restriction because otherwise you can just work with the inverse maps. So the only hypothesis here is that the center stable direction is absolutely continuous. If you have this hypothesis, then F is Bernoulli. Okay. And in the second theorem, this is for volume preserving partially hyperbolic diffeomorphisms with topological neutral center and center direction 1. If the center is orientable and F is essentially accessible, then either the disintegration is atomic or F is Bernoulli. So just to mention very quickly, this C2 is unnecessary, but I'm keeping here all along the talk to avoid any technical problems, but this works for C1 plus and C1 plus here. Okay, so just to recall what I mean by atomic here, I take a foliated box. In this foliated box, we have Rockland disintegration. So for each plate, we have a measure, probability measure, which disintegrates the whole measure mu restricted to this plate. And I say that the measure is atomic if for almost every x, the conditional measure gives a positive measure to some point. So that's it. I mean, you have an atom for this measure. And I say that it's leaf-wise absolutely continuous if for almost every x, the conditional measure is equivalent to the Leaf-Lebesgue measure. So it means that it's smooth inside the plate. No, I mean, here I'm just in the theorem, yes, sorry, but here I'm just giving the definition of the terms. Yeah, this is the volume. Yeah, sorry. So this dichotomy here inside this Bernoulli property, it's actually hidden that the center direction is leafwise absolutely continuous. And this kind of dichotomy, atomicity versus leafwise absolutely continuity, appears in some other contexts in the literature. No, no, they do not need to be. Yeah, I know that exponentially mixed implies Bernoulli. It's a recent, very good result from Hertz, Kanigonsky, and Dogopiat, I think. But no, probably there are several examples where it's not, probably, where it's not exponentially mixing. This is very strong. No, but exponentially mixing is a very strong property. So I guess it's easier to obtain examples that are not Bernoulli than examples which are not exponentially mixed. I guess. I guess. So this kind of dichotomy appears also in the work, for example, of Avila Viana Wilkinson for perturbations of time-one maps of geodesic flows, where they prove that either the perturbation has an atomic center or it is actually smoothly conjugates to, is smoothly a time-one map of an anosmic flow. And it's also very common for people to ask if this property, this atomicity property, is a perturbable property or not. So it's not. It's important to know that this property is kind of a dead end sometimes. You arrive to atomicity and sometimes you just don't know what to do with it. And the problem is that there are actually open sets of maps of partially hyperbolic diffeomorphisms where you have this property. And some examples were given by me, Tazibi, and Varão, where we have open sets of DA, of derived from anosmic diffeomorphisms, where the center direction is atomic. So you cannot just perturb this property and study the perturbations. Yeah, they are exclusive because here you have atomicity, and inside this Bernoulli property is actually hidden the absolute continuity. But I understand what you ask. I mean, here in the theorem, it's not. I mean, you can have Bernoulli in this first case, I think, the way I have put here, but the way I'm writing in the article, here it's written F, the center is leafwise absolutely continuous, and F is Bernoulli. So yeah, I'm not quite sure if he's asking on this context with topological neutral center property. Yeah. Yeah, yeah, exactly. Yeah. So in this context, I do not have examples of Bernoulli diffeomorphisms that fall in this case, but actually it's really hard to construct this kind of examples. I mean, about what? Yeah, with the volume preserving thing, no, I do not have. No, we do have examples of this type. Yeah, but I don't know if they are Bernoulli. Yeah, I don't. Or perturbations of time-one map, you mean? Yeah, but do you know if they are Bernoulli? I don't know. Yeah. Mhm. Interesting. Mhm. Yeah, that's yeah. Yeah, I don't know. It's hard. Maybe, yeah, maybe we can find some like weekly mixing example first. I don't know. I think okay, yeah. We need to think about it. I don't have. Yeah, no, but essentially accessible here, it's just to use your theorem just to have the Kolmogorov property. So yeah. Yeah, I want the key property. Okay, so I will try to be a little bit brief here. So let me just give some general lines on how to go from K to Bernoulli so that I can justify what those hypotheses means. Okay, so to go from K to Bernoulli, we have to use Ornstein theory, where we have to prove the very weak Bernoulli property. This is a very technical property, so I reduce it here to actually what we have to construct. Actually, we have to construct a sequence of partitions, which are refining to the partition of points. And such that for each of these partitions, if we take a path long enough, this is called path, even though it's forward iterates, because if you have a point here, you can trace the iterates of the past of the points. So if you take an atom in the far enough past, then this atom is very well spread along the manifold so that you can construct a map which goes from this atom to the whole manifold, such that this map compared to X, takes a point X, maps to another point, theta of X, which has almost the same itinerary of X for a lot of time. So this means that if you take the average of the names of those points with respect to the partitions F minus I of alpha and F minus I of alpha, but one of them restricted to the atom, these 2 points will belong to the same atom for most of the time. Okay, so this is what this map is doing. I take the index of this partition, which contains the point X, and this one, the index of this partition, which contains the point theta of X. If this index is the same, then this map, this function E will give the value 0. If this index is different, then it will give the value 1. So it just measures how far are these 2 itineraries, okay? And you want to construct a map which is almost measure preserving. It does not need to be measure preserving, but it's almost measure preserving. And it keeps this mean very low. So it's natural to think that if you can construct this map preserving stable foliations, then the point X and the point theta of X will remain very close when you iterate forward. Okay, if X is mapped to a point inside the stable foliation, then as you iterate forward, these 2 points get close to each other. And then by Birkhoff theorem and some justifications, then you can expect that X and theta of X will belong to the same atom for a long time. Okay. Okay, here we do not have just the stable foliation, so we need to guarantee that these points are close, even if we can construct theta, just preserve the center stable direction. And that's why the Lyapunov stability appears. So the argument goes more or less like this. You take the whole manifold, and then you partition this manifold by a finite number of rectangles. And by rectangle here, I mean a set that has product structure with respect to unstable and center stable. So if I take 2 points and I draw the unstable direction of this point, and the center stable direction of this point, they will intersect in one point inside the set. And then you take another partition alpha, which only needs to have this property. The boundaries should be piecewise smooth. You take any atom of this partition, and what happens is that as you iterate this atom, it will stretch along the unstable direction, and eventually it will start to cross this rectangle, this fixed rectangle. So as this cross this fixed rectangle, it's important to observe that most of the points will cross completely along the unstable directions. And the points that do not have this property, they will represent a very few volume of the intersection. Okay, so what we do is that we take the intersection which is U-tubular, which means that for every point in this intersection, the unstable direction inside this small part is exactly equal to the unstable direction intersected with the big rectangle. Okay, and we constructed the map theta first locally from this small rectangle to the big one. And how we do it? We take an arbitrary point x0, and then we take the center stable piece of this point inside this set, which I'm calling here E, and I construct any map which goes from this blue part to the whole center stable part here in R, which is measure preserving. So I can do this because these are two Lebesgue spaces, so you can just construct an isomorphism between these two maps, which is measure preserving. Okay, and now how do I extend this function to the whole subrectangle? I take any point y, and then I map this point down using the unstable holonomy. In this point, I use theta 0, and then I go back to the center stable direction of y using the unstable holonomy again. Okay, so here is where the absolute continuity plays a very important role, because we want this map to be epsilon measure preserving, and this is only true if you have a control for the Jacobian of the unstable direction here. And to control the averages of the itineraries, we need these 2 points, y and theta of y, to be very close to each other for a long amount of time. And this is where we use Lyapunov stability, okay? And then the conclusion follows from certain uses of Birkhoff theorem and density, etc. So all this comprises in this theorem. What we actually have to prove is that if you have a C2 volume preserving, partial hyperbolic, dynamically coherent diffeomorphism, then if the center stable is leafy-wise absolutely continuous and F has Lyapunov stable center, the K property implies the Bernoulli property. So actually, I spoke about absolute continuity of center stable in the previous slide, but by some technical adaptations, you can weaker this hypothesis to leafy-wise absolute continuity. No, yeah, you just need to bundle here. Yeah, it's center stable and unstable. Okay, so let me give a super quick idea of the first theorem, which is the GA case, the derived from a Nosov case. So just to recall, there we have a derived from a Nosov diffeomorphism of T3, and the only hypothesis we have is the leafy-wise absolute continuity of the center stable direction. So what is missing in the previous theorem is the Lyapunov stable center property. In this case, actually, we do not have this property, but this is solved because we have a semi-conjugacy between this map and the linear map, the linear Nosov map. And this semi-conjugacy has a very specific property, which is that it's not injective only along certain arcs of the center direction. So if you take a point, then the preimage of this point will either be just one point, or it will be a closed arc along the center direction. And this is very, very helpful because this set of arcs, they are invariant. So they will either have measure 0 or 1. And if they have measure 0, then the map H is injective almost everywhere. And because of this, we can take very large portions of the manifold, very large compact sets, and use the absolute continuity of H in this very large compact set and compare the distances along the center stable direction with the distances along the center stable direction of the linear part. And then this will give some kind of Lyapunov stability along very largest compact sets. Okay, so you do not have Lyapunov stability, but if you have that, that H is injective almost everywhere, you can take large portions of the set where you kind of have Lyapunov stability. If this set of collapsed arcs have measure 1, you can, we prove that you can actually find just one point in its interleaf where this whole set of points has measure 1. So here we have atomicity, but it's stronger than that. We have atomicity with exactly 1 point in its interleaf. And this is very important that we have just 1 point, because if you restrict your analysis to the set of atoms, then there are no 2 points which can be collapsed by H. And that's very important. If you have like 2 atoms, then you cannot have Lyapunov stability for large sets, because you can have 2 points which are different and still being collapsed. So in any case here, in any of these 2 cases, you can prove that you have very large sets where you have some kind of Lyapunov stability. The points can leave the set for a while and then come back. And the number of times that it leaves the set are very small, because you can take this set very large. So the density of visitors is becoming very large. Okay, so this is how somehow Lyapunov stability appears in this context, in this context. And in the second theorem, the starting point is the existence of the invariant arc lengths. So this arc length induces in a very natural way a system of distances. You just take the distance between 2 points to be the length of the simple arc connecting these 2 points along the center. This system is invariant, and we have proved that if you have this kind of distances invariant by F, then you have a trichotomy. You must have either atomicity along the center, or the center conditional measures will be equivalent to the measure given by the arc lengths. So the measure of an arc is just the arc length of that arc. Or you have a third possibility, the supports of the center should be Cantor subsets. But actually, then talking recently to Federico, we found a simple argument that shows that you actually have to fall in these 2 cases. It's important that the third case is not necessarily disjoint from the first one. So you may kind of have atomicity and at the same time the support being a Cantor set. Okay, this is not disjoint. Okay, so let me just show how we can go from this result to this result. How can we show that we actually fall in these 2 cases? So we consider a set of maps which are called central limit maps. This name was given by Bonatti and Zhang. So these maps are maps from a center leaf to itself, which are obtained by iterations of F. So you take a point X and you start to iterate. There's a subsequence which converges, and then you take this subsequence and defines a new map from the center of X to the center of X. So these are called center limit maps. And they proved that if you take the set of all the center limit maps from a certain leaf F, this will be a transitive group, and this will be actually isomorphic to translations on R or rotations on S1, depending if this leaf is compact or not. And maybe these maps are not all orientation preserving. So in this case, you have to add the minus identity as a generator, because then you need to consider reflections on the point. So with this subgroup, we consider a smaller subgroup of these maps, which are the center limit maps preserving the class of the measure. So you take all the center limit maps, which means the maps from the center leaf to itself, given by limits of F. But here we are taking the maps that preserves the class of the conditional measure. So it does not preserve the conditional measure literally, but it preserves the class of this measure. And we can prove that this is actually a closed subgroup of the previous one. And also that if you fix a point X, then for almost every point in the center leaf, you can construct one of these maps that maps X exactly to this other point. So in some sense, you have like as most points in the support, and it's not exactly the support, but you have as most points that are seen by the measure as you have this kind of maps, as you have center limit maps. And the thing is that this group, because it's isomorphic to translations on R or rotations on S1 and adding, if necessary, this minus identity, because of this, the support of this, it's not the, sorry, the support of the conditional measure will either be full, or there will be a countable number of points which have full measure for this conditional measure. Okay. Mm-hmm. Yeah. Mm-hmm. Yeah, because here I mean that, sorry, there is missing a mu here. Here it was supposed it's, yeah, exactly. Yeah, sorry, I missed the measure here. Okay, so the question is, with that previous result, we have reduced it to two cases. Either we have atomicity or the conditional measures are equivalent to the measure given by the arc length. But so the question now is the measure given by arc length equivalent to the Lebesgue measure? This is what we have to prove to conclude that the center direction is leafwise absolutely continuous, and then use this to conclude the Bernoulli property. So this is proven by kind of invariance principle, a local invariance principle of these measures. So if we have all this setting, C2, partially hyperbolic diffeomorphism, one-dimensional center, and topological neutral center property, and assume that the center foliation is again orientable, and here I'm putting that the orientation is preserved by F. In the previous theorem, we don't need that because we can take iterates of F. It will also be ergodic and it will preserve the orientation. And I take an invariant ergodic probability measure with full support. So here I do not need mu to be volume. Okay, it can be any probability measure. So there is a finite cover by local charts, where inside these local charts, if I take the restriction of the measure to local charts, either the conditional measures are atomic, or the disintegration along the center plates is invariant by stable and unstable holonomies. And the corollary of this result is that if I take mu to be smooth in the beginning, then the disintegration will be equivalent to Lebesgue. And this is because we have this lemma from Avila-Wilkinson, which essentially says that you start with a center local leaf, and you take a measure which here is called MP. You take a measure MP here, and then you will construct on the nearby center leaves measures given by taking this measure and mapping this measure by stable and unstable holonomies. So I first take this measure, and then I use the stable holonomies to map the measure in the center plate to measures in other center plates here. And then I use the unstable holonomy to take the measures in center plates down here and map back and map up to measures in other center plates. Okay, so at the end you get a system of measures, MQ, and if this system of measures is a disintegration of a Lebesgue measure in the local chart, then you can conclude that actually these measures are equivalent to Lebesgue. Okay, so let me just show very quickly how we can prove this local invariance principle. So you take a local chart constructed as before, as in the lemma of Avila-Wilkinson, and you take the disintegration on center plates in this local chart. So each local leaf, we consider parametrization of the center leaf with reference point X using the invariant matrix. So it's something. So you look to the center leaf, and then I will call this point R, for example, if this distance, let's see, is R. Okay, so I will just change the names of points. This is a parameterization of the center leaf with X being 0. Okay. So, and then I consider the normalizations of the conditional measures with respect to this parameterization. So I take the conditional measures giving measure 1 to a certain ball of fixed size. This delta here is just a value that should be small enough to guarantee that this ball is inside some local chart of my family. And for example, in particular, in this case, if I take the measure mu p, then this measure will be the measure that gives measure 1 to the ball centered in P and size delta, which is actually just the disintegration of the measure restricted to U. Okay, and then I take the Jacobian map. I consider the Jacobian at this point. So I will denote it by JXR. And this Jacobian is not with respect to Lebesgue, it is with respect to the leaf measure given by the arc lengths. Okay. And what happens here is that this Jacobian is actually invariant because the up measure here is invariant, and the measure given by arc lengths is also invariant because arc lengths is invariant. And the parameterization is invariant as well because it uses just the arc length to define the points. So I have this invariance almost everywhere, and it's important to remember that this almost everywhere is actually with R fixed. So for rational values of R, I have that this map is equal to some JR constant, okay? But it's not a priori for every R. And how do we solve this? How do we extend to every R? We just have to open a little bit the definition of the Jacobian. So if we open the definition of the Jacobian, we will conclude that it's a constant times the disintegrated measures evaluated on balls centered in XR, which is the point I called R, and on the point X. So this map is continuous restricted to a plate when we change X inside the plate of X, and continuous on R fixed X. So this is very technical. I mean, we had kind of not so nice time proving this continuous stuff, but this is just technical things. And then because of this continuity, we can extend this property to the whole plates. So we can find actually a full measure set inside this local chart, which is plate saturated, and such that inside this plates, the Jacobian is just depending on the parameterization. So it's the same for every leaf, not depending on X, just depending on the position of the point with respect to X. And then it's not difficult to show that if you take two plates and you consider the measure on this plate given by the disintegration of the measures of the local chart, and I'm using here the point P as my reference for the parameterization, then this measure should be mapped to exactly the measure in this leaf, because if I take an arc here, gamma, then the parameterization of this arc will be mapped exactly to the same parameterization here. So this R point comes exactly from another R point here. And because these maps are not depending on the point PL, then I will not go through this count, but this Jacobian will remain the same as you move along the stable direction. Okay, so it's not very difficult to show that actually this disintegration is SNU invariant, and if the leaf is not inside this set, this N set, then you can just define the measure by mapping the original measure by stable and unstable holonomies. And this system will coincide with the original disintegration. And then by using Avila-Viana-Wilson lemma, we conclude that the disintegration is actually equivalent to Lebesgue. And then by using the theorem C, I think, where I showed two conditions that imply the Bernoulli property. This is one of them. If you have FCS leafwise absolutely continuous and topological neutral center, then you have the Bernoulli property and we are done. Yep. So that's it. Thank you very much.
Are there any questions or comments?
'Hungry.
25 minutes to wait. Okay, well, let's thank the speaker again.